discontinuity, which we have talked about, a function is continuous at any value a if and only if the function value at a is the same number as the limit of the function as you approach a. So here I've given you an example of something that's not continuous. And the reason is because f of a does not exist, and the limit as x approaches a is what? 2. I should do it this way. So the limit as you approach a is 2, but the function value at a does not exist, and they don't match, so therefore they are not equal, and that's discontinuous. Okay, on the next exercise, what's f of a? 1. What's the limit as x approaches a? On graph B, what is the limit as x approaches a? Does not exist. Because from the left and from the right, it's different. So because these don't match, those are not equal, it's discontinuous for that reason. And on the third one, and a third example of discontinuity, what's the function value at a? 2. We're going to say, I didn't really label it, but yeah, good guess. F of a is 2. The limit as x approaches a is, oops, I didn't mean to put f of a, I meant to put f of x. What is it? 1. From the left, from the right, 1. So the limit exists, the function value exists, but they're still not equal. So it's discontinuous at a. Okay? So this one was discontinuous because the function value didn't exist. This one was discontinuous because the limit didn't exist. This one was discontinuous. They both existed, but they weren't the same. Okay? In this particular case, and it will make sense when I say it, this is called a removable discontinuity. Which is essentially, you could just plug up that hole and that would remove it. So these are discontinuities. This is technically called a removable discontinuity, when like almost just like one point is removed. So holes create discontinuities. Jumps, I'll call them. Jumps cause discontinuities. What other example of discontinuities don't I have here that I wish I had? What other visual? Let's add D. What other feature would cause a graph to be discontinuous? For bonus points? Winter? Asymptote. Good. You know what? Winter. Just because I appreciate that. Just because I'm feeling appreciative. And an asymptote. Exactly. So, I don't know. I'll just do something random. What's that? I don't know what you said. What approaches infinity? I don't know. When you just say something generic like it approaches infinity, never mind. So let's just kind of do what we did down here. What's f of a? Does not exist. What's the limit as x approaches a? Also does not exist. And even if they both went towards positive infinity, right, that still technically does not exist. So even though these match, you don't ever say that does not exist equals does not exist. You can't say that. So these still do not equal each other. And we have, I mean, testing continuity, when you have the picture in front of you, is so easy, right? It's clearly discontinuous at A because you can't, smoothly draw a line through it. The function has some sort of hiccup there. Whether it's a hole or a jump, another hole or an asymptote, it's much clearer to see whether or not continuity exists if you're looking at the picture. But again, the reality is going to come where we don't have a picture in front of us. We might have a function that we're looking at that we have no idea what the picture looks like. Yet we're supposed to address the issue of continuity with the definition and evaluating these two separate pieces of information and seeing if they match. Okay? So, first example, rational function. Is it continuous at 2? Let's see if we can figure this out without sketching. So, what is f of 2? So if you plug in 2, you get 4 plus 1, which is 5, over. Plug in 2 to the bottom, you get 2 times 4 is 8. 8 minus 2 is 6. 6 minus 1 is 5. What is the limit as x approaches 2? Now, on a basic rational function, where's the only place the limit doesn't exist? At an asymptote, right? Okay, just so knowing the nature of a rational function, the only place the limit wouldn't exist is at an asymptote. Everywhere else, direct evaluation works. Yes? So we essentially would directly evaluate to find the limit by plugging into, and we would also get 1. And so they do match. And so, yes. Is there any other discontinuity? Yes, Taylor, where? Okay, so essentially we have to figure out where doesn't this function exist? Where are the holes or the asymptotes? So if I factor the denominator, I get 2x and x, 1 and 1, minus plus. So there is a discontinuity, what'd you say? At negative 1/2, because this is a hole. That's because those cancel. That's my explanation, by the way, because it's a hole. And my work is obviously justification for why I know it's a hole. Where else? 1, because that's an asymptote. Any questions? So far, so good. Determine whether the function f of x is continuous at 2. At 1, are there any others? So same idea. Is it, and we'll justify our work. So starting with whether or not it's continuous at 2. What's f of 2? Does not exist. Right? You get 0 over 0, or you get negative 2. No, you get 0 over 0. Right? 0 over 0. Point doesn't exist. The limit then is not worth looking at. If either one of them doesn't exist, what? 0 over 0 is the indeterminate case if we're looking for a limit, but if you're just looking for a function value and you plug in and you get 0 over 0, that does not exist. There's no function point. There's no point at that spot. The limit might exist, right? If we when we get 0 over 0 and we're searching for the limit, we have to manipulate a little bit, and maybe once things cancel, the limit will exist, but the function value still just is not there. Okay? So if either the function value or the limit doesn't exist, you can stop your continuity hunt right there. It's definitely not going to be continuous if one of those doesn't exist. So, not continuous. You do not need to go and also search for the limit. So at 1, what's f of 1? What is it? 1/3. So 1 minus 2 was negative 1. 1 minus 4 was negative 3. So the double negative made the 1/3. Now again, by the nature of rational functions, if we're now going to look for the limit as x approaches 1, if 1 is not an asymptote and 1 is not a whole, and even if it was a whole, direct evaluation should work, yes? And so you would directly evaluate to find that. You get 1/3. Any other discontinuities is going to come from actually searching yourself. X minus 2 over x plus 2, x minus 2. So we have a discontinuity at 2, which we already knew about. We didn't do it, but now going back and thinking about it, would the limit have existed as we approached 2? Would it have? If once we factor and manipulate, it simplifies to this. Would the limit have existed as x approaches 2? Yes, and it would have been what? 1/4. Again, because of the nature of the question, we didn't have to go any further once we got that does not exist, but now that we've gone further anyway, it's worth talking about. And so, any other discontinuities? Where? Negative 2. Because that is an asymptote. Piecewise functions. Determine if and where any discontinuities are for the following functions. So, this is a line. It's only a partial line up until 0. Prior to 0, it's definitely going to be continuous just because lines are always continuous, right? This is a line. Lines are always continuous. So in between 0 and 1, we don't have to worry about any tweak. This is a quadratic parabola, right? So anywhere beyond 1, it's definitely going to be continuous because quadratics are always continuous. So as individual functions, these are all continuous. When it's piecewise, you have to be concerned with what's happening at your points of transition from one function to the other. So that would be at 0 and also at 1. So we'll start with 0. What is f of 0? 2. What is the limit as x approaches 0? Now, this might take 2 more pieces of work because there is a difference if you're coming at 0 from the left versus coming at 0 from the right. So if I kind of break this down, what is my limit as I approach 0 from the right? If I'm approaching 0 from the right, I'm using this equation, yes? So the answer is 2. If I'm approaching 0 from the left, I'm using this equation, yes? And the answer is also 2. So does the limit exist? Yes, those match, so it's 2. Now, because these match, is it continuous? Yes. I'll just say continuous. continuous. That's kind of, my yes is misleading because of the question. At 1, we're going to do the same thing. We're going to search for the function value at 1. What is it? 2. Our limit as x approaches 1 is going to take some work because we have to think about, well, what if we're approaching 1 from the left versus what if we're approaching 1 from the right? So as x approaches 1 from the left, we're using this equation, right? So what's that? What's the limit as we approach 1 from the left? 2. What's our limit as we approach 1 from the right? 3. So because those don't match, what's the limit? Does not exist. And now those don't match, so it's discontinuous at 1. So visually, what's happening here is there's your line x plus 2 prior to 0. Then from 0 to 1, we've got a flat line at 2, which would technically be an open circle and a closed circle, but this open circle is on top of what was already a closed circle from the first one. So those two pieces of the piecewise function come together, and then your third piece, when x is greater than 1, starts at 1, 3, and kind of does that. So we have continuity here at 0, luckily, it's kind of a lucky thing, and we don't have continuity at 1. We have a limit at 0. We don't even have a limit at 1. Any questions? Piecewise functions are a little bit tricky. You got to look more into them. And again here, as individual functions, that's always continuous, always continuous, always continuous. So anywhere less than 0, we don't have to worry about discontinuity. But perhaps right at 0, which is a point of transition, and right at 2 are our points of interest. So f of 0 is what? 0. And the limit as x approaches 0 is going to take a little more work. Okay? So as we approach 0 from the right versus as we approach 0 from the left. As we approach 0 from the right, we're using the second equation, correct? Which is 1. 0 plus 1 is 1. Honestly, we could stop there because to at least answer the question, because who cares whether or not the limit exists? If it's 1, then it's not going to match the function value anyway. But just for the sake of completing it, x approaching 0 from the left would be this one, so that would be 0. So the overall limit does not exist. And so discontinuous at 0. And then at 2, what's f of 2? 5. Limit as x approaches 2. Now, you could kind of, if you wanted to, maybe not show the work so much. 2 from the left is going to give you 5, and 2 from the right is going to give you 5. So since those are both 5, and they're all 5, everything's 5, we are continuous there.